have a chat about these distance time graphs, and I've done the old classic. I've set it up as like a 100 metre sprint race, because that's a really nice kind of motion to think about, to look at what might acceleration look like, what might constant speed look like, what might deceleration look like what might all these different types of motion look like when we plot them on a distance time graph. So, say you're quite slow at first in a 100, well, I'm quite slow at first in a 100 metre race, like first 20 metres could well take as much as 4 seconds, but I know that I'm picking up speed over that first 20 metres, and so the shape that we're looking at in a distance time graph as we're accelerating, if we're picking up speed, is that the gradient of the graph is going to be gradually increasing. And that works because the gradient of the graph is the speed. And so when you're accelerating, it might look something like that, a bit of a curve, and then once you've done those first 20 metres, you're a fifth of the way there. It tends to, you sort of go at constant speed until you get there. And I reckon 12 seconds is a good, honest time to finish the 100 metres in, and so constant speed for the remaining from the 4 seconds up to the 12 seconds. By that stage, you know you've made it to the finish line, and so we can slow down gradually for a couple of seconds, and then relax, celebrate, stop, maybe lie on the ground. And so this first section here, where it's curved, the curve shows acceleration. And then this section here, from 4 seconds up to 12 seconds, we've gone from 20 metres up to 100 metres. How far have we travelled in those 8 seconds?
80 metres.
80 metres. And so the straight line shows constant speed. What we have to be able to do though with a constant speed section is we've got to be able to calculate how fast they're going. And so the rule is that the speed is equal to the gradient. And how come does that work? Gradient is like rise over run. And if we look at the rise we're measuring distance, and the run we're measuring time. And so gradient, rise over run, distance over time, which is our equation for speed off our formula sheet, V equals d over t. And so a legitimate question that you might get in your exam was calculate the speed that was travelled during the section of constant speed in the race. And so we look at it and we're like, okay, speed equals distance over time. Speed equals distance. We've gone from 20 up to 100, so 80 over time. We've gone from 4 up to 12. Sounds like 8. Speed is 10 metres per second. 10 metres per second doesn't sound fast, except when we're gauging our metres per second, we remember that 27 is 100 k's per hour. And so it's like almost, it's a little bit over a third of the way to 100 k's per hour. So that's probably a pretty legit running speed. In the next section of the graph, we can see the downward sloping curve. That shows deceleration, or we call it acceleration, but slowing down.
That makes a lot of sense. Deceleration.
Yeah, well, deceleration is a word that comes up only in level 1 science. Then once you get to level 2 and level 3 physics, there's no such, you can't write deceleration, you have to write acceleration. You just say that it's slowing down. And then this last section, the horizontal line, shows that we're at rest. The distance isn't changing, but the time is changing, so horizontal line, at rest. And then our last and our trickiest piece of interpretation that we have to do from this graph is they could ask us, so how much is the acceleration like in this first section? So there's nothing that we can read off the graph that's going to show us the acceleration, but we can calculate it. So if we go to the formula sheet, so acceleration is change in speed over change in time. Looking at that first section there where we're accelerating, how much is the speed changed by? How much is that change in speed? How much was the speed at the start? And how much was the speed at the end? How much is the constant speed in that section there? 10. So how much is the speed changed by? It's gone from 0 up to 10. The change in speed is 10. So we could write it as acceleration is the change in speed is 10 over change in time. It's gone from 0 seconds up to 4 seconds. Change in time is 4. 10 over 4. 2.5. And accelerate. Does anyone know the unit for acceleration? Meters per second. We normally write meters per second squared. So this change in velocity thing here can sometimes be hard to work out what it is. And so a useful little rule is that the change in velocity is the final one minus the initial one. So final velocity was 10, initial was 0. So 10 minus 0 over 4. That might help if you're not sure what the change in velocity is. That might help to work it out. Questions about that? Okay, I think that's our new learning for the day.